Imagine you could prove you're over 21 without ever showing your ID, or prove you have enough cash for a purchase without revealing your bank balance. Now, this might sound like some kind of sci-fi magic, but it's not. It's real-world cryptography, and it's called a zero-knowledge proof. And this incredible idea has kicked off a high-stakes arms race to build the actual physical hardware for this new type of math. So let's dive in and break down what this race is all about.
So how on earth does something like this even work? Well, the best way to wrap your head around it is with the classic cave analogy. Picture this. There's a circular cave with two paths, A and B, and deep inside, a locked door connects them. You want to prove to your friend that you know the secret password to that door, but you don't want to tell them what it is. So you go into the cave and randomly pick path A or path B. Your friend, who's waiting outside, then yells out which path they want you to come out of. Now, if you know the password, no problem. You just open the door and exit from whichever path they chose. After you do this a few times, they become totally convinced you know the secret, but they've learned absolutely nothing about the password itself. That, in a nutshell, is a zero-knowledge proof. Pretty clever, right? And this seemingly simple trick is a total game changer. I mean, ZKPs are the key that could finally let blockchains like Ethereum scale to millions of users. They're the cryptographic engine that makes private transactions on networks like Zcash possible. They let us check if a complicated job was done correctly by someone else without redoing all the work. They can shrink an entire blockchain's history into one tiny proof like Mina does, and even help secure decentralized storage systems like Filecoin. The potential here is just absolutely massive.
Okay, I know what you're thinking. This sounds almost too good to be true. One piece of tech that gives us scalability, privacy, and security. There's got to be a catch. And yeah, there is. A very, very big one.
Here's the heart of the problem. Actually creating one of these proofs is a monumental task. We're not talking about something quick and easy. This requires incredibly intense math that can take minutes or even hours and eats up a ton of computing power. This computational wall has been the single biggest barrier stopping ZK technology from really taking off.
So, what's happening under the hood that's taking so long? Well, when you break down where all the time goes, two main culprits pop up. About 60% of the entire workload is an operation called Multi-Scalar Multiplication, or MSM for short. And the other 40%? That's taken up by an algorithm called the Number Theoretic Transform, or NTT. If we want to make ZK proofs faster, we have to figure out how to speed up these two specific operations.
All right, let's not get lost in a math lecture, but here's the basic idea. MSM is all about brute force. It's doing a gigantic number of multiplications on huge lists of numbers, which, as you can imagine, uses up a ton of memory. NTT, on the other hand, is more of a logistics problem. It's all about shuffling data around constantly. Think of it like trying to sort a massive deck of cards over and over again. It's not that the task itself is hard, it's that you're just constantly moving things, creating this huge bandwidth traffic jam on the hardware.
So if the bottleneck is fundamentally a math problem that pushes our current computers to their limits, the solution isn't just about writing smarter software. It has to be better hardware. We literally need to build physical machines that are custom-made for these very specific calculations. And that realization has kicked off a fierce competition, an arms race really, to build the perfect ZK-proving machine.
In this hardware arms race, there are really three main contenders, and each one has a totally different strategy for tackling the problem. Let's break them down.
First up, you've got the incumbent, GPUs, or graphics processing units. You know these. They're the powerful chips in gaming PCs and huge data centers. Right now, they're the default solution, mainly because they're powerful, you can buy them today, and they're flexible enough to get the job done. They're the established workhorses of the field.
Next in line are FPGAs, which stands for Field Programmable Gate Arrays. You can think of these as the specialists. They're this interesting middle ground, not as all-purpose as a GPU, but you can actually program them at the hardware level to be super efficient at specific things, like, for instance, speeding up those MSM and NTT operations that give you more focus and more power with a bit of flexibility left over.
And finally, we have what most people consider the ultimate solution, the ASIC. That's an application-specific integrated circuit. This is a chip that's designed from the ground up to do one single thing. It can't do anything else, but it does that one job faster and more efficiently than any other piece of hardware on the planet. And in this race, that one job is generating zero-knowledge proofs.
Okay, now this is where it gets really interesting, because this table lays out the crucial trade-offs. GPUs are your baseline. They're available right now today, and they give you pretty good bang for your buck. FPGAs, well, according to the teams building this stuff, like Cysic, they're about as power efficient as a GPU, but they just can't compete on cost. And then you have the ASIC. It promises the absolute best performance per dollar and the best performance per watt. It's the undisputed champion of efficiency. The only problem, it can take 12 to 18 months, sometimes even longer, just to design and manufacture one of these chips.
And honestly, this quote from Cysic really says it all. While GPUs are the tool everyone's using today, and FPGAs are a powerful but maybe niche option, the entire industry seems to agree on where this is all headed. The long-term endgame for speeding up ZK proofs is custom-built ASICs.
And this chart, wow, this chart shows you exactly why everyone is chasing that ASIC dream. The performance jump is just staggering. If you move from a regular computer CPU to a GPU, you might get a nice 10x speed up, not bad at all. But when you move to purpose-built hardware, an FPGA, and especially an ASIC, we are talking about 100x or even 1000x acceleration. That's not just an improvement, that's a complete transformation of what's possible.
So, why does any of this matter? Why should you care about this hardware arms race? Well, because winning it is what takes zero-knowledge proofs from being this slow, expensive, niche thing for crypto nerds to something that's fast, cheap, and widespread enough for everyone. It means all those promises we talked about, scalable blockchains, truly private finance, verifiable computing, can finally stop being theory and start being a practical reality that we all get to use.
And this leaves us with a pretty wild final thought. We are literally watching people build physical infrastructure for a branch of abstract math. For decades, we've had chips for graphics, GPUs, more recently specialized chips for AI, and now we're building chips for cryptographic proofs. So as we forge this direct link between abstract equations and physical silicon, you just have to wonder, what entirely new applications and what new kinds of digital worlds are we about to unlock?